Hey guys, it is time for the electricity and magnetism review. This unit starts with electrostatics. So we'll talk about some basics, atomic structure. What particles make up the atom? Well, you know, it's the electron and the proton and the neutron. And the proton and neutron are what we call nucleons because they are in the nucleus. And the electron is in the electron cloud. And they orbit the nucleus. Okay, so you have the nucleus in the middle with the protons and the neutrons, and the electrons are in orbit around. What does it mean to say that charge is quantized? Well, the amount of charge that the proton and the neutron have is 1.6, I almost forgot, times 10 to the minus 19th coulombs. The coulomb, C-O-U-L-O-M-B, is the SI unit of charge. And a proton has positive 1.6 times 10 to the minus 19th coulombs, and the electron has negative 1.6 times 10 to the minus 19th coulombs. And charge comes in this quantity or multiples of that quantity, not in any other. You can't have, 1.2 times 10 to the minus 19th coulombs because this is the quanta of charge. Charge is quantized. How would an object become negatively charged? Well, okay, so protons are in the nucleus. You can't take them out. If you take a proton out of the nucleus or you add a proton, you change the element. Remember, that's the atomic number. So it's electrons moving around that cause things to be charged. So if you want something to be negatively charged, you have to give it extra electrons. So you would add electrons to it. And if you want something to be positively charged, you remove electrons. So something that is positively charged has a deficit of electrons. So it has more protons than electrons, not because it gained protons, because it lost electrons. And something that's negatively charged has extra electrons, not because it lost protons, but because it added electrons. The fundamental rule about charges interacting, well, you know what that is. It's opposites attract. And likes repel. You will have to do calculations on the quiz and the test that look like this. How much charge is on 2.24 times 10 to the 13th electrons? Well, the total, if each electron has this much charge, and we call that charge, this quantity, we call it E. If you want to know what the total charge is, it's just going to be equal to the number of electrons times the charge on one electron or proton. Okay, so if you have an amount of charge and you want to know how many electrons that is, then you would divide the amount of charge by the charge on one. So you can rearrange this equation, but the total charge that you would have would be equal to the number of electrons that you have times the charge on one electron. A conductor is, well, kind of simple. A conductor conducts electricity easily or well. Charge moves easily through a conductor. Metals are typically good conductors. They are good conductors because they have loosely, can't spell loosely, L-O-O-S. This is embarrassing. Their outer electrons are loosely bound. O-O-S-E-L-Y, L-O-O-S. I think it has the E in there. I'm a physics math person, not a great speller. That's not an excuse for you guys. Everybody should be able to spell and write, even if you're great at math and science. Insulators, now I can spell this. Insulators have tightly bound outer electrons. Do you get summer brain? I kind of get summer brain. So someone watching this video not in the summer is going to think that's a dumb comment, but for those who are watching in spring or fall, I'm creating this video in July. An insulator is a material that doesn't conduct well. It resists the flow of charge. And sometimes we call materials made of insulators resistors. Examples of insulators: wood, glass, plastic. You can think of a lot of them, I'm sure. How do objects become charged? Well, you have to move electrons from one place to another. So you either add electrons or you take electrons away. And there are 3 different ways we can do this. Friction is when we rub 2 objects against each other, one pulls electrons off the other. If you've ever done laundry and pulled the laundry out of the dryer and the clothes are sticking together, it's because you have dissimilar fabrics, and some of the fabrics have an affinity for electrons and they pull electrons to themselves, and others, their electrons are more loosely bound and they'll let them go easily. You rub these 2 dissimilar materials together, the one that can give up electrons will, the one that can gain them will, and they'll become oppositely charged and they'll stick together. Conduction happens when you have a charged object and you touch it to an uncharged object, and they share. Charge runs off of the charged object onto the uncharged object, and they both end up charged. Induction is a little bit more complicated. Luckily, you don't have to know too many details. A charged object is brought near an uncharged object. Then the uncharged object is grounded so that it gains a charge. So an example of this, I'll say this as quickly as I can, is an electroscope. An electron typically has a metal ball, a metal rod, and it has 2 little very thin pieces of metal, like aluminum or gold. A good one will have gold. And a lot of times you'll see them in an Erlenmeyer flask and stoppered, so that these things are so light and thin that air will move them around. So if I bring a big negative charge towards this electroscope, it's going to cause the electrons that are evenly spread out all over this metal sphere, metal rod, metal leaves. It'll cause the electrons to run away. And so the electrons will end up down here. And actually what you'll see is, if I can redraw that electroscope, you will see those leaves spread apart. That's why the electroscope is in an Erlenmeyer flask, to give room for those leaves to spread. So if the charged object, the big negatively charged object, is still there, these will stay negatively charged and they'll stay spread. If you ground it, connect a wire here and run that wire to ground, and this is the electrical symbol to ground, and that would be like connected to something metal, or a wire that goes to the grounding hole of a socket. If you do that, it allows these negative charges to run away. Instead of being down here, they'll run away. And what you'll see happen is I'm going to change my color here. These things will droop back down. But then when I take the negative charge away, I end up, here's my electroscope. Then these will spread back apart because now they're positively charged because the electrons left. Okay, so this would be charging by induction. Induction, there is no contact, there is no rubbing, it's the other way. A charged object is brought near an uncharged object. The uncharged object is grounded so that it gains a charge. In this case, it lost electrons, but that means it gained a positive charge. Okay, charged particles exert forces on each other, and here we go. And you can calculate the force that they exert on each other by using an equation that we call Coulomb's law. And Coulomb's law says that the electric force between objects is equal to a constant K times the amount of charge on each object, Q is the symbol for charge, divided by the square of the distance between their centers. The value K is 9 times 10 to the 9th, and that would be newtons meters squared per coulomb squared. Okay, so 9 times 10 to the 9th is K, so it's a really big constant. This is an inverse square law. It's got the distance squared in the bottom. So if you double the distance between your 2 charges, you don't reduce the force by a half, you reduce it by to 1/4 of its value. So an inverse square. Of what is the force between, I'm going to set this up, but I may not do the calculation. We'll see. So F equals K Q1 Q2 over R squared. So the force will be 9 times 10 to the 9th times 2 charges. Now we use the absolute value of these charges. You determine the direction based on whether you have opposites that will move towards each other or like charges that will move away. So you answer the two parts separately. So you don't put in the -8, you just put in 2 and 8. Sometimes you see this equation written and it has absolute value bars around those two quantities. They are 2 meters apart, so 2 squared, and let's see, 2 squared, calculator on, so 9, 10 to the 9th times 2 times 8 divided by 4 equals 3.6 times 10 to the 10th. Newtons. How would you solve for distance or for charge? Well, this is my equation. If I want to solve for the charges, Q1, Q2 would equal the force times the square of the distance divided by K, right? Move the K to the bottom and move the R squared to the top. And if I wanted to solve for R would be the square root of, move this R squared over here, and the force goes to the bottom, K, Q, Q1, Q2, over whatever the force is. And you will have to solve for those other variables. Sometimes they'll, in a problem where they ask you to solve for the charges, they'll tell you they're the same. And if they are, then this, instead of being Q1, Q2, it would be Q squared. If Q1 and Q2 are the same, then Q1 times Q2 is Q squared. Okay, I'm sure you'll practice with the content. Electric charges have electric fields around them. It's an area of space around a charge where another charge would feel a force, like a gravitational field. The gravitational field is an area around a mass where another mass feels a force. Gravitational field lines always point towards the mass. Electric field lines point away from a positive charge, but they point toward a negative charge. It is the direction that a positive charge would be moved. And if I put a little positive charge right here, it would be pushed away from that blue positive charge. If I put a little positive charge right here, it would be pulled towards that negative charge. So the definition of the direction is the direction that a positive charge would be moved. These are examples of other fields. If I have a negative and a positive charge, the field lines look like this, going from positive to negative. They actually make big loops. These would all join. This would join up with big loops around it. If I have two positives or two negative charges, I get a zero field right in between. This is a field between a charged plate and a point charge, and this is a field between two charged plates. We use these a lot in physics and electromagnetism discussions. To calculate the strength of an electric field, it is the force that it causes divided by the charge, and the force on a charge in an electric field is equal to the electric field strength times the amount of charge. This is very much like F equals mg. G is our electric field strength. This is you could put a little subscript E by that force, the force of an electric field, and this is the gravitational field force. And the gravitational field strength is equal to the force that it causes divided by the mass. So see, they look very much the same. The electric field strength is the force that the field causes divided by the charge, and the gravitational field strength is the gravitational force divided by the mass. Okay, the electric field is a vector quantity, and the force is a vector quantity. The force is in the same direction of the field if the force is on a positive charge. See, if let's draw this field here, field around a positive charge. And let's put a little positive charge here, and we'll put a little negative charge here. So the force is in the same direction of the field if you're on a positive charge. Well, that makes sense, because this little positive charge over here is going to be pushed away from the other positive charge. So its direction will be in the same direction as the field. This little negative charge, it's going to be pulled toward that big positive charge. And so the direction of the force on it is opposite the field. Electric potential energy is just like gravitational potential energy in many ways. Objects that have mass in a gravitational field have gravitational potential energy depending on where they are. Objects that have charge have electric potential energy when they're in an electric field. It's energy, it has units that are joules, and it's also equal to the work done moving the charge in the field. And there are quiz questions that ask exactly that. The potential energy that a charge has is equal to the work done moving that charge in an electric field. For a proton, if you move a proton in the direction of an electric field, it loses energy. That's like if you move a mass in the direction of a gravitational field. That would be like dropping an object. It moves along the field lines that point towards the Earth, and it loses potential energy. If you look at this picture, if you think about this positive charge down here, to move it towards this positively charged plate would take work. It wants to get as far away from those other positive charges as possible, so it will naturally move down. To move it up requires work. To move it up then would increase its potential energy. To move it down along the field lines would be a decrease in potential energy. For an electron, it would be different. The electron wants to move towards that positive plate. So if I move it against the direction of the electric field, it loses energy. If I move it in the direction of the magnetic field, it gains energy. So think about this structure. Where does the charge want to be? If it moves where it wants to be, it loses energy. Just like if you drop a ball, it moves towards the Earth and loses potential energy. Electric potential energy is equal to negative QED, Q being the charge. So if you plug a negative charge in there, you'll have two negatives. E is the electric field strength, and D is the distance. And if you move it in the direction of the field, it's a positive distance. If you move it opposite the field, it's a negative distance. So you could have three negatives altogether in this equation. It's also equal to negative force times distance, which is negative work. So the change in potential energy is the opposite of the amount of work that you do. Equivalent in magnitude, but opposite in sign. If you do positive work on it, you'll get a negative change in potential energy. To store energy in a battery, and there's a question like this that you'll have to answer. To store energy in a battery, we move electrons in a direction opposite the electric field to do work on them and to store that chemical energy in the battery. Electric potential difference. It's a little bit different than electric potential. The electric potential difference is the energy per unit charge. And so you calculate it. It's also voltage, the same thing, and the units are the voltage, and the symbol is V, and the potential difference or voltage difference is the change in potential energy per unit charge, the change in potential energy divided by the unit charge. What's the change in potential energy if you move a charge of 6 coulombs through a potential difference of 12 volts? So if I rearrange that equation, the change in potential energy is equal to QV, and that would be 6 coulombs through 12 volts, and 72 joules. You will need to be able to do calculations with this equation as well. The potential difference, like see these parallel plates right here? There's a distance between them, D, from one plate to the other, and there's an electric field that has a certain field strength. You'll need to be able to calculate the potential difference at positions between these plates using potential difference is electric field strength times distance. So if I move a positive charge from here to here, and I wanted to calculate the electric potential difference, I would multiply the electric field strength by the distance that I moved that charge. What is the potential difference between parallel plates if V equals 3.5 newtons per coulomb and D is 0.2? So if V equals ED and E is 3.5 newtons per coulomb and D is 0.2, then you get 0.7 volts. Okay, so the 22 got left in there from my traditional classroom, but now we're going to talk about current in circuits. Electric current is the rate of flow of charge. It's the ampere, and an ampere is 1 coulomb per second. And you may have to do calculations with this. What is the current if 3 coulombs of charge travel by a certain point in 2 seconds? So, well, that would be 3 coulombs of charge over 2 seconds would be a current of 1.5 amperes. Conventional current is the flow of positive charge. So in physics, when we talk about a current, we're talking about a flow of positive charge. Even though we know negative charge is what's moving, it's been the convention since we knew that, and nobody's changed it. So it is the flow of positive charge. Charge flows for 2 reasons. Because there's a potential difference. There has to be some force pushing them. Like a ball doesn't just roll, it rolls downhill from a high potential energy place to a low potential energy place. So there has to be some potential difference and a complete circuit. Or a closed circuit. Batteries provide the energy that moves the charges through the circuit. Batteries have a potential energy between, if you have a 3-volt battery, that's the potential difference between one side of the battery and the other, and that means it provides 3 joules of energy for every coulomb of charge that goes through it. So batteries give you that potential difference, give you the energy to push the electrons through the circuit. You should be able to find current. We already talked about this. If you're given charge and time, you need to be able to find current, and we actually just did an example of that. Some materials provide resistance to current flow, and we use these materials to regulate current flow. And a resistor will look often like a cylinder. It doesn't have to, but it'll often look something like this and have wires to connect to. The resistance depends on the length, the area, and by area, I mean the cross-sectional area of the resistor, temperature, and the material. Longer length means greater resistance. Resistance, the symbol is R. The unit is the ohm. The symbol for the ohm is the Greek letter omega. The bigger area, well, the fatter it is, the easier it is for current to flow. The bigger the area, the smaller the resistance. Temperature, the higher the temperature, actually the higher the temperature, the higher the resistance. If all those particles, the higher the temperature is, the faster the particles in a substance are moving, vibrating. And if all of those particles in there are vibrating, it's harder for the electrons to get through. So high temp means higher resistance. And the material, different materials have different resistivity. P-I-V-I-T-Y. And this isn't in this course, but in another course you may see it, and the symbol for that is the Greek letter rho. And the higher the resistance of a material, the higher its resistivity. So depending on the material that you make, with the same length, area, and temperature, it would have a higher or a lower resistance. Ohm's law says that in a circuit, the current in that circuit is directly proportional to the voltage and inversely proportional to the distance. Big voltage, big pressure pushing the electrons, big current. Big resistance, a great difficulty of current flow, small current. We typically write that V equals IR, though. Electric power, just like in the work, energy, and power unit, it's the rate at which work is done or the rate at which energy is converted. In electricity, we calculate it, P equals IV. Power is current times voltage. Also, if you use Ohm's law, remember Ohm's law says V equals IR. And so if I is V over R and P equals IV, and if I replace that I with V over R, then I get V over R times V, or V squared over R for power. And if I solve for resistance, resistance equals voltage over current. And in the P equals IV equation, if I replace the voltage, V equals IR, I don't need this, I need this. if I replace voltage with IR, then that gives me IR, which is I squared R. So V squared over R and I squared R are two other ways to calculate power, and the units are still watts, just like in the previous unit. Circuit diagrams. We like to draw nice, pretty pictures of circuits, simple, clean, orderly diagrams so that we can see what's happening more easily. The symbols that we will use for a cell, it is a short line followed by a long line. And the short line is the negative side of the cell, and the long line is the positive side. Okay, so I usually just call that a battery. Technically, a battery is several of these, two or more. And so this would be a battery, this would be a cell. And again, the long side would be positive and the short side is negative. So you have some questions about this on tests. The single pair is a cell, multiple pairs together is a battery. A voltmeter is used to measure voltage, an ammeter is used to measure current. When you put those in a circuit, a voltmeter has a V in it like that, and an ammeter has an A in it like that. A resistor, or a device that uses the current, is a zigzaggedy line like that. We'll see some better pictures that I didn't draw soon. Like right there. There are two types of circuits. The first is a series circuit, and this is a series circuit. You can tell because if I leave that battery and I go all the way around the circuit, I never have an option. There's a single path. This is the diagram here that matches this picture. We replace the light bulbs with the symbol of a resistor, and here's our cell. And so we have 3 resistors in series with a cell. No breaks, no options, no other path than just that single path. In a series circuit, the current is the same everywhere in the circuit because there's only one path. Voltage of the battery is shared by the devices, and the potential difference of the devices added together equals the battery voltage. The bigger resistance, the larger the potential difference. So in this circuit, the 40 ohm resistor uses more energy than the 30 or the 20, and so the potential drop across it, the potential difference across it would be bigger than for either of the others. The things you would have to find with a series circuit: the equivalent or total resistance and the current in the circuit. For a series circuit, the equivalent resistance is just R1 plus R2 plus R3, or however many resistors you have. So in this problem, it'd be 20 ohms plus 30 ohms plus 40 ohms, and 20 and 30 is 50, and 40 is 90 ohms would be the equivalent resistance. And then finding the current in the circuit's easy, because current is equal to voltage divided by the resistance. And in this problem, voltage in the circuit is 20 volts, and divided by 90 ohms. Get my calculator. 2 is 0.22, 0.22 amperes. If these are light bulbs, what happens when one burns out? Well, if one burns out, what happens is the filament, which is that little resistor part, actually breaks. And so you would have a break in the circuit and current couldn't flow. So if one light bulb burns out, they all burn out in a series circuit. The second kind of circuit is a parallel circuit. And so here's a picture, 3 light bulbs. Notice they kind of are all connected directly across the battery. That one's connected across the battery, that one's connected across the battery, and this one's connected across the battery. So they're all connected directly to the battery, so each of them would have a 9-volt potential difference across it because they're all directly connected to the 9-volt battery. In a parallel circuit, the voltage across each device is the same. The current in each branch is equal to this voltage divided by the equivalent resistance. In each branch would be equal to 9 volts divided by the individual branch resistance. For example, the current in this branch right here would be 9 volts divided by, that's 10 kilo ohms. Let's just pretend it says 10, take the kilo out, do that in all of these. For the whole problem, we're just going to take the kilo out. So 10 ohms, 2 ohms, and 1 ohm. 9 volts divided by 10 ohms would be 0.9 amperes. And so the current in this branch would be 0.9. And you can calculate the other branch currents as well. But so the currents depend on the resistance of that resistor, but the current through battery is what you're going to have to calculate. And then you just divide the voltage of the battery by the equivalent resistance. We'll do that for this problem. Okay, equivalent resistance or total resistance for parallel circuits, very, very different than series. 1 over the total is 1 over 1 plus 1 over the other plus 1 over the third. And so 1 over the equivalent resistance is 1 over, we have a 10 ohm, 2 ohm, and 1 ohm. 1 over 10 plus 1 over 2 plus 1 over 1. Now, you can find common denominators if you want to, but I use the inverse button on my calculator, and I suggest that you do. And so 1 over 10 1 over 10 is 0.1. 0.1 plus 1/2 is 0.5 and 1. So 1 over our equivalent resistance is 1.6. But we need the inverse of 1.6 to find our actual resistance, and the actual resistance is 0. If I do the equivalent resistance is 1 over 1.6, I get an equivalent resistance of 0.625 ohms. Just heads up, the total resistance will always be smaller than your smallest resistor. So when I saw a 1 ohm resistor there, I knew that my total resistance would be less than 1. Okay, so we know how to calculate the equivalent resistance and the current through the battery. That's easy. I is V over R, and so 9 volts divided by 0.625 and divided by, not 0, oh, it's 0.6, and divided by, it's 14.4. And okay, I'm just going to tell you, this is a whopping lot of current. 1 ampere of current is deadly. Current, the ampere is a huge unit of current. So 14.4 amperes, that would be really, really bad for you. So we have series circuits and parallel circuits and combination circuits. What you have to do is look at this circuit and see that these two things are in parallel, and they're in parallel because they are connected. The ends are connected together, and then that parallel unit is in series with R1. So you have to find the equivalent resistance of the parallel part first, and then find the resistance of all of it together. So let's do that. Let's pretend that R2 and R3 are 4 ohms. We have 4 ohms here and 4 ohms here, and R1 is 6. Let's let the battery be a 12-volt battery. So R2 plus R3, 1 over the equivalent resistance is going to be 1 over 4 plus 1 over 4, and that's 2 over 4. So the equivalent resistance for those is 4 over 2 is 2 ohms. So now we've reduced that circuit to something that looks like this, 6 ohm resistor, and this with a 2 ohm resistor, and then back up to the battery. So now we find this is R2 and 3. So now to find the equivalent, the total equivalent resistance, it's just going to be 8 ohms. 6 plus 2. Okay, and now to find the current through the battery, it's going to be I equals V over R, and that's 12 volts divided by 8 ohms, and 8 will go into 12 1.5 times. 1.5 amperes, and again, even 1.5 amperes current. Okay, if it had been 2 series things in parallel with one thing, there's the battery, we would add these together using the series rule, and then I'd have 2 resistors in parallel, and I would add them using the parallel rule. Magnets. Magnets have 2 poles, north pole and a south pole. You can't have a monopole of a magnet. I mean, you can talk about this being a monopole, but there's no, it's kind of like 2 sides of a paper. You can't have a piece of paper with one side. Paper comes with 2 sides, and magnets come with 2 poles. It's just how they are. Opposites attract, likes repel. And what would happen if you broke a magnet into pieces? If I broke this magnet into two pieces, I wouldn't have a north pole here and a south pole here. I would have a north pole here and a south pole here and a north pole here and a south pole here. I'd break into little tiny magnets. I have broken ceramic magnets before and had actually little things that kind of look like this, and they were all little tiny magnets, little slivers, bits of magnet. The Earth has a magnetic field. Scientists think that it is caused by the rotating core of the Earth. What is interesting is that our geographic North Pole would actually be the south pole of a magnet if it were caused by a big bar magnet. And it is the south magnetic pole. The south geographic pole is actually a north magnetic pole. So when our compasses point north, they are a compass is made of a needle with a north pole of a magnet here and a south pole of a magnet there. And when the north pole points north, it is because it's attracted to that south magnetic pole at the north geographic. All magnets are caused by moving charges. It can be a spinning electron, which is why iron atoms are little magnets, a current in a wire, which is a moving charge, or an electron in a wire that's being moved. So if you physically move a piece of metal, you can, if you physically move a piece of metal, you will generate a magnetic field. Note that magnetic field, that should say lines. Magnetic field lines point away from the north magnetic pole and toward the south magnetic pole. It's the direction that a north pole would be pushed. And so if I put this compass needle, well, you can see the little compass needles, the little white parts, the north pole, and the north pole is pushed towards the south magnetic pole. The unit of magnetic fields is the Tesla. So why are iron and other ferromagnetic materials are materials that are all magnets for the same reason, and they're easily magnetized. And iron is ferromagnetic. Ferro means iron. And so the deal is, every little spinning electron spinning on its axis, has a little magnetic field. The symbol for magnetic field is B. But typically, if you have two electrons near each other, they have opposite spins. And I'm going to put plus and minus B, although they're not really plus and minus, but their fields cancel. So a pair of electrons have their fields cancel. But iron and other ferromagnetic materials have unpaired electrons, so that their fields are going in the same direction, their magnetic fields are going in the same direction, and their fields add. So every iron atom is a tiny magnet because of the spin. A piece of iron is not necessarily a magnet because the spins of nearby atoms will cancel. Iron and other ferromagnetic materials end up getting divided into domains. So in this little domain right here, the magnetic fields are aligned to the right. So all those little atoms influence each other, and the magnetic fields are aligned to the right. But in this domain, they're aligned up, and in this domain, aligned to the left. So this would be an unmagnetized piece of iron or other ferromagnetic material. If I put this in a magnetic field, what it causes is most of the domains to align. And now I've got a magnet. I've got all these little magnetic fields now aligned in the same direction, making a big magnetic field, and that piece of iron is magnetized. Moving charges in magnetic fields experience forces. Now, we will learn to calculate the force on a moving charge in just a minute, but we're going to learn how to find the direction, and we do that with some right-hand rules. There are two of them. The first helps us find if we have a moving charge or current in a magnetic field, helps us find the direction. Now remember, the current is a current of positive charge. Right-hand rules work for positive charge. So if I have a positive charge moving, if it's moving through your room, just imagine the room that you're in right now, and the positive charge is moving from your right to your left. So look at your room from that wall that's to your right to that wall that's to your left. And the magnetic field is pointing from the ceiling to the floor. The magnetic field is pointing down, and the velocity of the charge from your right to your left. So that would be right, left. Point your fingers towards the floor. Point your fingers in the direction of the magnetic field. So that would be having your hand, so that your fingers, not a very good hand, but okay, so here's your wrist and arm and everything. So your hand's going to point down because the velocity is put your fingers to the floor because your fingers are the direction of the magnetic field. And now turn your hand, rotate it so your fingers are still pointing down, but your thumb is pointing towards your left in the direction of the velocity of the charge or the current. And what that leaves, so I'm going to do it, if I have my fingers pointing towards the floor and my thumb pointing towards the left, then my palm is actually pointing towards me, or pointing towards the wall behind me. And that is the direction of the force on a positive charge. It would be towards me or towards the wall behind me. If that charge was negative, then the force would be away from you, towards the wall across from you in your room. You can either use your left hand for a negative charge, or you can use your right hand rule and just flip 180 degrees the direction of the force that you get. If you want to calculate the force on that moving charge, the force is equal to the charge quantity times the velocity of that charge times the strength of the magnetic field. You will have to do that on quizzes and tests. The other right hand rule, the other time we need to know the direction of the magnetic field, because of, well, it's a current carrying wire. Here's a wire, the current's moving up. It is a positive current, conventional. The direction of the field around it is concentric circles, but it's not just circles with no direction. They have a direction attached. Notice here, if you look down on this, would be counterclockwise. And we get that by wrapping or imagining that we wrap our hand around the wire with our thumb in the direction of the current. The direction of our fingers indicates the direction of the magnetic field line. Okay? In this diagram, if the current flowed down, if instead of I being up, I was down, the field direction would switch. These little arrows would be going the other way. Also, if we're an electron current up, it would also create a field that was clockwise, opposite the direction of this. So negative things, if you have to find the direction of the field caused by an electron current, use the right-hand rule and then change the direction. Electromagnets are magnets that are made from electricity. They can be as simple as this picture here, where I just have a nail and a wire wrapped around that nail a bunch of times and a battery. The current, the moving charge, generates a magnetic field. And a moving charge in a straight wire has a magnetic field, and if I bend that wire and make loops, it intensifies the field inside. And if I put an iron core, it intensifies the field even more. So this is a picture of a loop, current out, current in. Current goes through all those loops and generates that magnetic field. The strength of the field is directly proportional to the number of loops. I double the loops, I double the field strength. And also directly proportional to the current, and putting the iron core inside makes the field stronger. Generators and motors are very similar. This is a picture of a generator and a motor. Michael Faraday determined that if you move a wire in a magnetic field, a current will be induced or generated in that wire. In the picture, if I had a crank handle like here, and I were able to turn that and make this loop rotate in this magnetic field, there would be a current. I could put a resistor here or a light bulb. Let me do that. I could put a light bulb here. Here's the filament of the light bulb. I could put a light bulb here and the light bulb would glow, not grow. Moving this wire in that magnetic field would put a force on all of the electrons in the wire, and they would move through a completed circuit. On the other hand, if you take this battery and you put the battery here where I've drawn the light bulb, and you make current go through the loop will turn. So if I am putting mechanical energy in, if I'm taking that motion and generating electricity, I have a generator. But if I use the battery to provide the current, if I provide electrical energy and I get movement, mechanical energy, electrical energy to mechanical energy, I got a motor. Same parts, but make different products depending on how you use it. In the free response questions at the end of the test for this unit, make sure that you can use all of the equations that I have presented. Coulomb's law, electric field strength is force per unit charge, voltage is electric field strength times distance, potential energy is equal to negative QED, which is also equal to negative QV. You also need to be able to find equivalent resistances for series, parallel, and combination circuits, and the total current in series, parallel, and combination circuits. Study hard and you should do really well on this test. I hope you found this review to be useful.